Good evening, everybody. So today, Dmitrii Rudenko will speak about the Kaggle competition on detection of the gravitational waves. So thank you very much that you agreed to make a talk. Please start.
Thank you, Alexander. So today we are discussing G2 Detecting Continuous Gravitational Wave competition. You can follow the link to get slides if you're interested. Everything is shared. I'm Dmitrii Rudenko. I'm data scientist for almost 5 years, and we got a bronze medal with Stas at this competition. So let's look at the leaderboard. We will discuss top 3 solutions and our solutions at the 61st place, which got us a medal. You also can follow me at LinkedIn and Stan at LinkedIn or Kaggle, don't know. Right now I'm a student in Ludwig Maximilians Universität. If you're in Munich, call me for random coffee. So the task. The task was to figure out if we have a signal in recording of gravitational wave sensor. Unfortunately, the data was mostly synthetic. Why mostly? Because we had some real noise examples in test and trained data sets. The main part of the data was generated with SpyFstat2 using generation of noise and separately the generation of signal. And after it, we had to join this and create our own training data sets to solve the competition. So the part of the competition was to generate your own data. Data also included real noise, split it into several parts, and artificial signal was added at every test to generate semi-synthetic data. So let's start from the bottom. Our solution was mainly based on Vladimir Slaykovsky public kernel. I also asked him to join us today. So if you've seen him in chat, you can ask him a lot of questions about it. But the main idea was the following. He played with 5 stats and created several thousand signals and several thousand noises. Joining it with random weights helped him to create a training data set, which was pretty nice to use for training. It had a nice distribution, very similar to the test set. The tricks we used we added more folds. We used yet another neural network, another architecture. We added early stopping for every fold, which Vladimir didn't. One round of pseudo-labeling helped us to achieve better score. We could use 2 rounds and get better results, but it was kind of unconservative, and we stick to our model, not to overfit, not to shake down. A lot of people were shaken down. We jumped from 90th place to 61st. And also we used manual labeling. It took us about 10 hours. 5 for me, 5 for Stas. Stas was mainly solving this competition from his cell phone. So yeah, just greet him. That's a weird story of success. We also found out one important thing at this basic kernel. Vladimir was generating real, like, synthetic noise and tests on the fly, randomly choosing with repetitions the signals and noises. So we just improved his result by sampling more data with the same approach. We didn't stack anything, so it's very basic solution in these terms. But the first place solution is even easier, and like, it's genius. The author just extracted frequency and power from every recording, just statistics, no real recordings. Subtracted Doppler shift from every value and assigned weights to each record based on the absolute amplitude of this record. Then he summed up the results with a technique called power summation and tried different strides for every recording, keeping the best one by the maxima of power sum. And he also checked out every test set with every test set, like pairwise, to find out which one is better. And that's all. It took about 5 days of GPU A100 to compute it, but it took the first place. You can click at the top one solution to read more about his approach. Let's keep the distance. The second place solutions is pretty the same. Guys were sampling random signals every iteration from special distributions they estimated. The thing was that 5stat just needs 2 or 3 parameters to generate another signal, and they did it. They found out the best parameters for random search. After generating random signal, they matched it with every test set with different strides. And by these statistics, they got the best result. So at the end, they had a best result for every test set. And by this histogram, they managed to find out the optimal threshold to figure out which sample is noise and which one has signal. And the third place solutions, finally, some deep learning approach. It's a big team, mostly American one. People did the following. They found out that training set has 2 different types of, or test set has 2 different types of signals. The one which had a noise with normal distribution, and the second one with chi-squared distribution. So that's the leak they found, which helped them at the end. They generated 40,000 samples of noise, signals, and glitches by manually labeling the samples. We found out that there are some glitches, but we didn't manage to find out if it's really glitches. We were wondering, why doesn't these samples count towards signals? We were thinking that that's signals, but it was just glitches of detectors, and it was a part of a noise. So the idea was the following. They took some samples from the test, generated their own noise to augment it, and added their synthetic signal. And that's how they created a lot of training sets strapped in this manner. These sets were really balanced, like 1,000 of pure signals and 1,000 of pure noise. They also improved their neural networks with denoising layers. And they used hierarchical stacking, which had such an architecture. They trained some models only at the real noise data, which they defined by glitches and like chi-square distribution. And they trained several models on synthetic data. After that, they stacked it with multiple bootstrapped regression models and got just the mean of every parameter, and that was their like final prediction. And that's all I wanted to say today. Join my Telegram channel. It's in Russian, but you can still read the follow-ups of this competition there. Ready to answer questions.
Thank you very much. So, colleagues, please don't hesitate to ask questions. And may I ask a question? So it was something like images, yes? So the input data was what?
I see. The input data was just fast Fourier transformation based on fast time Fourier transformation of signals, but it like was able to convert all the training data to images, and we were solving it as a images competition. But two first places were doing this like another thing. They were playing only with signals. Every sample contained two layers. The first one for real part of transformation, and the second one for imaginary part of transformation.
And how big was the sample? Each sample?
Every sample had more than 4,000 units length and kind of 800 units like height, but we could like reduce the size of it by just removing several parts, because every point of this matrix were highly correlated with each other.
I don't quite understand. So you say each signal was 4,000, something like in one direction and about 400 in the other. But what are these directions?
Like time direction for 4,000 and the quality of it, the like resolution of it was kind of 800.
But if you say signal typically is something like one-dimensional, but here it's a kind of two-dimensional, but not the image. So I'm not quite.
Yeah, I see. Yes, these detectors has like multi-dimensional coverage. Like it's two detectors, and every detector records like without any stop. So yeah, you have to reduce, and these detectors have different frequency rates. So every detector generates a lot of data at the same moment.
So something like one is time, another is frequency.
Yes, yes.
Okay. Okay. So at the current slide, we see these images, and on one of the images, we see such a kind of a line, which is kind of noise, or I don't know.
Yeah.
It is what is it?
Yeah. Okay. The horizontal line is gravitational wave, but vertical lines are just the detector's noise, which is distributed as chi square. So yeah, the last team also was using denoising technique, which helped them. They got median filtering by the columns of this signal.
So and what was the task? So we have this data which we represent as an image, and so the task was binary classification. Is there?
Yes.
Okay, and the metric was area under the. Okay. So and how many images? How many samples?
It had 8,000 samples at test set, and at training set they had kind of 1,000. But like as I said, a part of the task was to generate several train sets for yourself using PyFstat.
What was PyStar? It's some special package.
Yeah, it's a special package from developers of this competition, which is also used as simulator of signals by the G2 network. Yeah, which solves the task of gravitational waves analysis.
But so these gravitational waves are real wave or it's simulated?
At this competition, we had only simulated waves, but some part of data had like real noise from the detectors. Yeah, but mostly it was synthetic data competition, and that's why first and second place got such a good results in it, because they kind of reversed back the competition data generation pipeline.
But there was something in physics kind of great news several years ago. They claimed that they finally observed the gravitational waves. Is it the same team or it's another story? What detectors are the same, or it's a different technology? Or
I see. Yeah, gravitational waves were found using these exact detectors, but we still didn't manage to detect any neutron spinning star signal. And the idea of this competition was to like simulate neutron spinning star signal and try to figure it out.
And we cannot observe these signals from the neutron stars because they are very weak, or because kind of so the idea is that they are very weak, and we must develop this technology which will help to solve this problem, or it was something different.
As far as I see, these signals are pretty rare, and usually these signals are digged inside the noise. So here we were trying to undig the signals and improve the signal to noise ratio using machine learning.
But so.
But we didn't observe any real neutron spinning star signal yet. So yeah, we just beaten with simulation how physics understand how should these signals be.
Ah, okay. I see. Okay, you mentioned word glitch or glitch and something like that.
Glitches.
Glitch. What is it?
Like, oops, the wrong scene. I can show you, I bet, somewhere at the competitions data we had. No, not that one. Let me find one. The third place solution might be here. They've shown it in their data. Or it in EDA. Let's try to find it in EDA. Coach. Blah blah blah. EDA. This one mightn't be too well. That's the wrong one. Oh, damn. Let's see. Something. It might be somewhere here. Okay, let's say glitches is just outliers in terms of signals. It's very hard noise, very hard signal, which is even higher seen in terms of frequency. And that's why you cannot like figure out if it's nice one or if it's signal or not, because it's too hard. And usually it is somehow connected with just detector noise. Something happened, like electrical break, which made it operate like irrationally, something like it.
Okay.
I'm trying to find the one for you, but still like cannot. Yeah, but feel free to ask another questions. I'm just finding out the proper example.
Okay. So colleagues also don't hesitate to ask questions, please, or comments or suggestions, whatever. On my side, if you can go to the slide where you describe the solution of the first place solution in your competition.
Okay, I want to get back.
Yeah.
Yeah, the previous one, this one.
So extract frequency and power from recording. What does it mean? Because it's a two-dimensional. It's a kind of image, so I don't quite. So what I.
Yeah, I see. The author just created the following things. He has a two-dimensional high-resolution image, and he just computed statistics by each axis, like by the vertical axis and the horizontal one. And that's all he needed to compute the distance between several images.
What kind of statistics?
I really don't understand this one. because it's full of physics. But yeah, you can keep track about it at his public notebook.
Okay, assign the estimation of the proportion.
We also tried to do something similar, like to find out how close signals are in test. But the thing we were using were BYOL, like beyond your own latent. It didn't work. It was always overfitting because we were pre-training it on the test set and then trying to fit it to the train one. So yeah, it didn't work. It always converged at the first epoch and didn't work. So yeah, there were an easier way.
The item 3 here says that so the final word is signal. Assign weights, blah blah blah, signal. But how does he define the signal?
I bet I meant like the difference in distribution there, because every signal has different frequency and amplitude of recording. Yeah, it's all about recording. It's based on recording's absolute amplitude.
Recording, what does it mean?
Like that's a recording.
Okay. Image, it's the same. No.
Yes, every signal recording. Yeah. Here
Yeah.
it's like transformed to the image, but originally it's not an image.
Okay. Okay, then some standard questions for Kaggle. So how much time did you use for it, for the competition?
I would say we were solving it for nearly 3 weeks, like several hours a day. We have manually labeled all the data set at the one weekend, just yeah, straight 5 hours. But yeah, I would say we were solving it for 3 weeks at least.
Okay, I see. And what hardware did you use? Some special hardware except of Kaggle or?
No, we were only using the Kaggle's resources. Yeah, mostly the neural networks were computed at mine resources, but my Kaggle resources. But a valuable part was done by Stas.
Okay. And resources, there was some standard Kaggle machine with 16 gigabyte of memory, and the GPU was limited to something like 30 hours per week, or they had some, for this competition, they gave you more powerful virtual machines?
Oh, just standard one.
Okay.
I also managed to improve my optimization skills because like optimizing, for example, data loader improves the speed of training by 30%, and this 30% of time are very valuable when you have limited resources of GPU. So it's very important to like write optimal code which would run faster.
Okay, I see. And so if we think of this as an image, so the kind of first idea to use something like a convolutional network.
As we did. We used EfficientNet V2.
Sorry, it was pre-trained something, or you trained?
Yeah, I see. No, it wasn't pre-trained because we have just 2 channels at this competition, and there is nothing pre-trained for just 2 channels. You can try 1-channel network or 3-channel network, pre-trained on, for example, ImageNet, but here we were training from scratch.
Okay. And another standard question. So if you look on the general solutions, not only top 1, 2, 3, but just what participants use and describe in the discussion forum, was it a neural network mainly, or there was kind of how various were ideas?
Yeah, people was mainly using something like the third team did. They was training neural networks, but as far as I see, like there was some lack of ideas at this competition. People was just trying to boost this Vladimir's public solution, but not everyone managed to improve it. Also, Vladimir dropped down from the leaderboard from the 30th place to 193rd or 2nd. Just he wasn't interested in getting a high score. He was just fighting for medals for like kernels.
Yeah, I see. He's doing it in many competitions. He provided some ideas, and the others can do them.
That's how the thing is done at Kaggle. That's why Kaggle has its own forum. You just use someone's ideas and improve it.
Yeah, that's great that people can learn from it. What was another standard question? Shake up. What was shake up? Was big or not?
I would say if you are not doing something very strange, you wouldn't shake up at this competition because data is synthetic and it was randomly split into private and public part. So yeah, public score and private score are highly correlated. But for some reason, people overfitted at the for the public leaderboard, like 50. Yeah,
Okay.
we got shake up from 90th place to 60th, but it's a tough thing. My friend was shaked up from exactly close place, like 80th to 47th place. And we had exactly same score as the public leaderboard.
Can you please show the slide with the leaderboard, or just the leaderboard? So how big was the difference between the top solution? Okay.
Yeah, they had a great solution, but like starting from the place 10, people have very close difference.
Okay.
But yeah, top places had a high speed. Also, Space Coders team was beating everyone for almost 2 months of this competition, and only at the end they were dropped down a little bit. But I believe they used something like the first place, some physics-based approach. And also, I would say thank you to Sean PI, if I'm right. He shared that he is using some physics-based approach. We didn't manage to like really improve it, but the idea was nice and winning one. Thanks him for sharing.
Great. Okay. Thanks. And so probably final question from my side. So what you enjoyed, what you learned, what for you was most kind of interesting, exciting, and useful?
So I'm really excited by such things as you can even get Kaggle's competition from your cell phone, as Stas did. Like, just be hard. I've learned a lot about PyTorch code optimization, which helps you to like get better results at Kaggle because you are iterating faster. WandaDB is very helpful, like weights and biases. Yeah, feel free to use it to track experiments. It also helps to like compare and share models. And I would say pseudo-labeling is very great technique. Use it everywhere. Compared with stacking, stacking is also good. That's it.
Okay, thank you very much. So, colleagues, any kind of questions, suggestions, comments? Stas, maybe you want to say something to add to your teammate? Don't hesitate. Okay, so thank you very much, Dmitrii. It was quite interesting. Thank you very much, and it's great that you got a Kaggle medal. And so it's a competition. I'm thinking it was quite hard because it's physics and some I don't know. For me, it was kind of I don't know. I didn't want to enter it because it's a kind of quite far from my domain knowledge.
Yeah, it was like I don't have any real experience in signal processing. I had just one silver medal 3 years ago with computer vision, but like I'm not specialized in computer vision. I believe that computer vision is like too specialized for me. I'm trying to be kind of wide side data scientist. So yeah, that's not that hard. That could be just try and validate your ideas, and you will get one.
Okay, thank you very much. Any questions, final comments or suggestions? Okay, then thank you very much again.